Hey everyone, in this video I wanted to start covering the animation blueprint and, well, the whole Locomotion setup for the Lyra starter game project, which was released by Epic along with Unreal Engine 5 as an example of pretty much an entire small example game created with the engine. We're going to start with the event graph, and as you'll see here, it's empty. Completely empty except for a single comment here explaining that the logic that would normally be run in an event graph can be found in the BlueprintThreadSafeUpdateAnimation function, which is a part of, I'm pretty sure, a part of the anim instance class in Unreal Engine 5, and it is overridden inside of this blueprint. The reason that they did this was because that the regular event graphs of animation blueprints are updated sequentially for each tick, meaning that if you have a bunch of different animation blueprints running, there could be a performance bottleneck because all the event graphs need to have their logic executed one after the other. Logic in the BlueprintThreadSafeUpdateAnimation function can be run in parallel. So I'll go ahead and double click to open it. Now that we're inside, we can see that there's another comment here explaining a node that I had my first encounter with inside this animation blueprint. I'm not sure if it was inside of Unreal Engine 4 or if it's new to Unreal Engine 5, but I wasn't aware of its existence until Unreal Engine 5. And it is the PropertyAccess node. And this comment explains the reasoning for using it quite well. Reading straight from it, it says this function, which is referring to the BlueprintThreadSafeUpdateAnimation function, is primarily responsible for gathering game data and processing it into useful information for selecting and driving animation. A caveat with thread-safe functions is that we can't directly access data from game objects like we can in the event graph. This is because other threads could be running at the same time and they could be changing that data. Instead, we use the PropertyAccess system to access data. The PropertyAccess system will copy the data automatically when it's safe. So then they provide an example of a PropertyAccess node where they access the pawn owner's location. And it shows an important feature of these PropertyAccess nodes is that you can essentially call functions from them. So if I just search PropertyAccess, I click the drop-down menu, we can, for example, there's a getMovement component function that was created for this animation blueprint that can be used to get to access all the different value returning functions for the movement component, as well as its variables. It should be noted that a function will only show up here if it has an output titled return value. You can actually take a look at that getMovement component function. It's just using a PropertyAccess for it, and it's calling the function try_getPawnOwner, and it's getting the movement component, and then it casts that to a character movement component and returns that as its return value if the cast was successful. So heading back over into the BlueprintThreadSafeUpdateAnimation function, we have a series of functions here. But I do want to, before we hop into any of them, bring your attention to this isFirstUpdate boolean. Its default value is set to true, and once, well, the first update finishes, it's set to false. And this boolean is used in some of these functions, essentially just to make sure that any variables that are dependent on the difference between the variable's value last tick and the value that it's going to be updated with on the current tick are set to 0 on the first update because otherwise those values would be inaccurate. So this first function here is update location data, and it does exactly what it says. It uses PropertyAccess to get values such as the actor location of the owning actor. Sets a displacement since last update, we'll come back to that, but then after that it sets a world location. But before it sets world location, it reads world location. It actually subtracts world location from getOnlyActor.getActorLocation. It gets the vector length of that vector, the two-dimensional vector length of that vector actually, and then it sets a variable that is displacement since last update. And the reason for this here is that, well, let's just go through an example. For our current tick, our actor location is 100, and for our previous tick, it was 80. And I'm just using a single value. Of course, this is a vector, it would have 3 values, but what we can do with a single value would apply to all 3. So we have our value of 100, we subtract 80, because even though our value is 100 right now, we have not yet set the world location function. It's still using the value from the last tick. We get the length of that vector, and we set displacement since last update. So this is a super useful technique to get the difference over a tick in pretty much any variable. And then right after this is set, we set world location so that is updated. Then we have this little bit of math here that is dividing the displacement since last update variable by the delta time variable, which is an input into the function here. And it's using the safe divide node, which just returns 0 if the denominator is 0. And so then displacement speed is set. But now, what if we're on the first tick? Well, again, we use this is first update, and we set displacement since last update and displacement speed to 0 because, well, when we do this bit of math here, world location does not have a value, so whatever it returns, whatever it sets this variable to is going to be an inaccurate number that doesn't make sense because it's the first update, it's the first tick, there has been no displacement in between this update and the last one, so this should be set to 0. And the same should be true for the current displacement speed. Update rotation data is a very similar function. It's just getting some necessary values for the rest of the blueprint to function, having to do with rotation. There's a yaw delta since last update, which uses that same technique as the location function did, where it's using this world rotation variable before it's set to get the difference in specifically the yaw between ticks, and then also again divides by the delta seconds to set the yaw delta speed variable. It's also checking whether or not the character is crouching or aiming down the sights to affect the additive lean angle. And then again, if it is the first update, it sets both of these variables here to 0. You'll notice that this boolean here is titled gameplay tag is ADS, which stands for aiming down sights. And so there's another thing I want to very briefly touch on here, and it is gameplay tags. Now, I'm not going to go into much depth here, but if you open up project settings and search gameplay tag, you'll pull up this gameplay tags section. And tags are, well, essentially just tags. You can give them categories and names, and you can assign them to actors or actor components. And it's essentially a way of keeping track of, you can use them to keep track of pretty much anything. So one example is aiming down sights tag. You could, of course, inside of your character component, create some sort of boolean variable that could be set to true if you're aiming down sights. Gameplay tags essentially serve the same purpose, but they do it in a cleaner, more efficient way. And they have their own set of functions that you can use with them to read through the gameplay tags an actor has and see if it has one of the tags or doesn't have one of the tags. There's just a whole lot you can do. The gameplay ability system uses them extensively, and Lyra uses the gameplay ability system. So that's one of the reasons why there are so many here. But it's a super useful feature, and if you haven't been using them, you definitely should. I didn't truly see the value in them until I started using them myself. Continuing from the BlueprintThreadSafeUpdateAnimation function, we have this update velocity data function and this update acceleration data function. Again, these functions are pretty much the same thing. I'm not going to continue to go over each and every little bit of Blueprint code here in each of these, but in this update velocity data, I do want to cover this section here, where it is taking a local velocity direction variable, which is a enumerator of the type anim class cardinal direction, I think, which is the enumerator that was created for this project, and you can find it right here in the animations folder. And it just has 4 enumerations: forward, backwards, left, and right. Enumerators really do just can be used the same way you might use an integer, but it's easier to keep track of things because you can give the enumerations names. The cardinal direction is what the Lyra animation blueprint uses to figure out which animations to play in many cases, at least when it comes to directions, such as forward, backwards, left, and right. Lyra does not use a classic 2D blend space in blend between lateral movement animations. Instead, it switches between them and uses orientation warping to bridge the gaps that those animations don't cover, which are the 90 degrees between each of them. And we'll be covering the orientation warping stuff in the video I do on this project, where we cover the anim graphs inside of this system. I'll go ahead and open the function up here, and the logic is fairly simple. It's actually a much simpler approach if you've watched any of the distance matching stuff that I've made on my channel, or any of the stuff I've been doing more recently in my streams. I really wish I would have thought of this approach. It's much simpler, and it's much more logical than mine was. So we're taking the angle, we get the absolute value of the angle, which is, if we look back at this function, is this value, this variable here, local velocity direction angle with offset. It says with offset because it is getting the difference between it and the root yaw offset value, which is used to offset the rotation of the mesh when the character is standing still and the capsule is rotating, so that when you start moving forward facing the camera direction, you move forward, you don't rotate into it, which is just used for handling turn in place stuff. And then this local velocity direction angle is just your standard direction variable, but it's given a more specific name. Heading back into the select cardinal direction from angle function, we'll continue to go through it here. There is a dead zone input, which the default of it is, I believe, the default's 10. And this essentially, when it has a value, it adds an extra buffer onto the forward and backward directions so that it favors playing those animations over the right and left animations. And now we have a sequence. The first thing we're doing is we're checking if we are using the current direction as an input for the function. And if that is true, we have a switch on anim cardinal direction node, which of course you could use this from any enumerator. It's a super useful node. And if we're moving forward, we double the forward dead zone. It should be harder to leave forward when moving forward. When moving left/right, the dead zone will be smaller, so we don't rapidly toggle between directions. And the same applies to backwards. Then after we do that, which we only do if we're using the current direction as an input, we then check if we're moving forward. And my approach was to do essentially the logic to check if we're moving forward, if we're moving right, if we're moving left, and if we're moving backwards sequentially. But I didn't consider that if we're not moving forward, we only need to check. We can sort of if we need to, we can subtract that logic out if we can. A great example of it is here. If we've checked all three of these conditions, so we know the only direction we have left is left, so we just know that if this is false, we're moving left. My approach was to then again do the whole entire big check as if we were checking to see if we're moving left first. So going through the logic here, we are adding 45 degrees to the forward dead zone and checking if the absolute value of the angle is less than or equal to this value. So let's take an example here. So let's say our absolute angle is 0. We're going completely straight forwards. And so our forward dead zone is, the default is 10. Let's use that. So we have 55. 0 is less than or equal to 55. And so we set our direction to forward, meaning that we have a range of 55 degrees on both sides of 0. So from negative 55 to 55, because this is the absolute angle, a negative 55 will be treated like a 55 in this equation. It'll be a 55 in this equation. So for that total of 110 degrees, we are moving forward. And actually, if we are using the current cardinal direction as an input and taking that into account, we have a total of, I think, 130 degrees here. And then, of course, if we're not going forward, we're going to check if we're going in the other directions. In this case, we check backwards next. So it's a very, very similar approach, except we're just using the backward dead zone. And so the exact same thing is happening here. We're just subtracting 135 instead of adding 45. But if we're not going backwards, we know that we are not going forwards or backwards, meaning that if our angle is greater than 0, we're going right, and if it's less than 0, we're going left. We don't need to check to see if we're in between whatever our maximum value of forward is and our minimum value of backwards, because we know we're not in between those already. So it's a much more efficient way of going about the calculation. And, well, that's it for the select cardinal direction function. And here we set it again, a new variable with the local velocity direction angle value variable instead of the local velocity direction angle with offset variable. And then we just set our other velocity related variable here, such as has velocity. Oops. Now heading back into, again, BlueprintThreadSafeUpdateAnimation, we have this update acceleration data function. Again, we're just getting acceleration related values all the way up until here, where, it is an acceleration related value, but there's a bit more complexity here. We are calculating a cardinal direction from acceleration to be used for pivots. Acceleration communicates player intent better for that purpose than velocity does. And the reason for that is that velocity is affected by things such as ground friction. It's not going to immediately switch when you switch inputs. If my understanding of the character movement component is correct, the acceleration vector is being applied to the character as a force, and then you have things like ground friction being applied and onto that, and the result of that whole equation there is your character's velocity. Because acceleration isn't being affected by all these other values, all these other parameters, acceleration is a direct reflection of the player's intent. Before we follow this logic through for an update or two, let's think about this acceleration value. If it is and because there are some things to really consider and keep in mind here as we try to understand this code. The most important thing being that a pivot is when you switch your acceleration and when there's an extreme change in the direction of your acceleration. Your acceleration is pointed in one direction, and then is pointed in another direction. Maybe sometimes that's almost instantly, other times maybe you just stop your input, but before you stop, you then switch to going the other direction. In that case, a pivot would still trigger if you have enough speed. Let's look at that first example where your acceleration just switches really fast. Sure, maybe it is 0 for a couple of updates where A and D if you're using a keyboard and you're not pressing A or D and you're in the process of switching. But again, we're just going to pretend that it's possible to do an instant switch where you are holding down one key, then the next, and there's not any point in time where you're not holding down either or holding down both, just to keep this simpler. So we have pivot direction 2D, which by default is set to 0. We're lerping that with an alpha of 0.5 with the normalized world acceleration 2D. So let's say that we have an acceleration of -1 on the x-axis, and because we're normalizing this, the length of this vector is always going to be 1. So we're lerping between a vector with 0 for x, y, and z, and a vector with 1 for x, 0 for y, 0 for z, with a value of 0.5. So our output is going to be -0.5. We're going to normalize that, which will give us a -1 on the x, and we set pivot direction 2D to -1. Next update comes around, barely any time has passed, it's almost just an instant. Our pivot direction 2D is -1. Let's say our world acceleration 2D is still, let's say that it is still, if our world acceleration 2D is still -1 on the x, after it's normalized, we're going to, again, just get -1 again. We're normalizing this. That 0.5 becomes a 1. Now let's say we pivot. Our world acceleration 2D changes from 1 on the x, -1 on the x to 1 on the x. Well, now we are lerping with a value of 0.5 between pivot direction 2D, which is -1, and normalized world acceleration 2D, which is +1. We're going to get 0. We're going to normalize that. Pivot direction 2D is going to be 0. Next update comes around. Pivot direction 2D is 0. World acceleration 2D is 1. Again, I'm just talking in terms of the x-axis. We're pretending there's no movement along the y-axis. So now we're going to get a value of 0.5. That's going to be normalized to 1, and pivot direction 2D is going to be 1. And so that is what this function is doing, setting this pivot direction 2D value, which is then being used to calculate a direction with the world rotation as the base rotation input. Then that is being run through a get opposite cardinal direction function to set the cardinal direction from acceleration. This really, I think, comes into play when you aren't pivoting 180 exact degrees. Because now every update you get halfway closer to your target rotation. If it's 135 degrees, for the first update you're going to be halfway between, well, whatever your current direction is, and 130, but your direction would be 135 degrees away. Next update, you're going to be even closer. Next update, you're going to be even closer, and that's going to continue to happen. So it's essentially a way of smoothing out that transition in a controlled manner. At least that's my understanding of it. It doesn't really apply much when it's an instant switch, but when it's like a 135, 140, 150 degree pivot, this has more of an effect. At least that's my understanding of it. If you guys understand it differently or have a different theory on why this is implemented the way it is, let me know. I'd love to hear it. This get opposite cardinal direction function is just using a switch on anim cardinal direction, and it is returning a value based on the input cardinal direction. Nothing complex there. And now we are finally through our update, just setting our base variables that we're going to be using throughout things for our sort of movement locomotion values like location, rotation, velocity, acceleration. Now we're on to wall detection stuff. And this bit of blueprint code here is a really simple way of detecting whether or not you're running into a wall. It's just testing if if there's a large angle between velocity and acceleration. So if the character is moving at a wall, chances are you're going to be sliding sideways, either left or right. But your acceleration, your input, is going to be pushing forward. That's a large enough difference that it will notice and realize you're probably running into a wall. It also checks if the character is trying to accelerate, but speed is relatively low, again because force is being applied to the character, which is hitting a wall, and you're just slowly sliding left or right because of that. So a super simple way of doing it. Don't think I would have thought of that. I haven't tried implementing any sort of wall detection logic in any of my stuff yet, but my first approach probably would have been to try to do some sort of trace. But that is a much simpler way of looking at it, and it's just another reason I'm super glad that Epic put together this example and released it to us, because there are things like that, things like the way they calculated cardinal direction, things are implemented in really effective, optimized ways here. A lot of those ways are things, and a lot of the time they're not methods of implementation that I would have thought to try from the get-go. So now we're updating character states data. We're using property access to get whether or not we're moving on the ground. We're checking whether or not we're crouching to set a was crouching last update. We're checking if we're crouching from the character movement component to set an is crouching variable. And then we're checking whether or not we've just switched our crouching state by checking whether or not is crouching is equal to was crouching last update. We're also getting these gameplay tag booleans, which we'll find where they're set later on, and doing a very similar thing here. And we're taking this gameplay tag as firing. If it's true, we're setting time since fired weapon to 0. If it's false, we're getting the value of time since fired weapon, adding delta time, and setting time since fired weapon. Then we have our in air state. We're getting the enumerator movement mode from our character movement component, which is a default variable, a part of the component, checking if it's equal to falling. If that is true, we're then checking if our world velocity z is greater than 0. If that is true, we set is jumping. If that is false, we set is falling. So if it's greater than 0, it means our velocity is up, we're jumping. Less than 0, our velocity is down, we're falling. And we reset these both to false before we check this, so that each and every tick, if we switch between jumping and falling, there is never a point where we're both jumping and falling. And of course, if this is false and we're not in this falling state, these are both false because we're not in the air. Now we have updates blend weight data, which is upper body dynamic additive weight being interped to 0 with an interpolation speed of 6. And then we have 1 here as another input and actually in a select float. And we're just checking if any montage is playing and if we're on the ground. And if both of those are true, then our value is 1. But if it's false, we interpolate between this upper body dynamic additive weight and 0. So it creates a smooth transition from 1 to 0. Oh, wow. Not sure if you guys can hear that, but I just heard some thunder. Looks like it is about to, or looks like it's either storming nearby or starting to storm here. Can't hear any rain, though. Moving on, we have this update aiming data function. Super simple. We're getting the pawn owner, getting base aim rotation dot pitch, normalizing the axis, which is just setting, it takes normalizing the axis, which just takes a degrees on a range of 0 to 360, and sometimes due to some math you might get like 370, which would just be 10 degrees. But anyway, it just takes that and normalizes it to negative 180 to 180. Next we have update jump fall data. So if we're jumping, if that's true, we get world velocity z, subtract it from 0, divide it by gravity, and set and predict. It's essentially we're predicting our time to jump apex. And if it's false, we set our time to jump apex as 0 because we are not jumping. So essentially, this is just a function of velocity and gravity that returns the predicted time to the apex of the jump. It looks like I accidentally skipped over this update root yaw offset function, so let's hop into that. This function handles updating the yaw offset depending on the current state of the pawn owner. So when the feet aren't moving, so during idle, offset the root in the opposite direction to the pawn owner's rotation to keep the mesh from rotating with the pawn. So the character is going to usually, in this sort of setup, the character movement component is going to have orient rotation to movement set to false to enable strafing, and then the character itself is going to have use controller rotation yaw set to true, so that when you're moving, you move your mouse around, you turn to face your mouse, or you move your camera around, you turn, and you're always facing the direction of your camera. It's a shooter, you're holding a gun, that needs to be happening. But that means that when you are idling, you turn your camera, your character just rotates around. And, well, that's a problem. You don't want your character spinning in circles while you're looking around. Sometimes you might want your character to stand still, and then other times you're going to want the character to play a turn-in-place animation and then rotate to match the facing of the camera. So in this case, we are rotating the mesh to counter the rotation of the capsule of the pawn. Based on this root yaw offset mode enumerator. We're setting root yaw offset through the set root yaw offset function. It's clamping the offsets because at large offsets the character has to aim too far backwards, which over-twists the spine. The turn-in-place animations will usually keep up with the offset, but this clamp will cause the feet to slide if the user rotates the camera too quickly. If desired, this clamp could be replaced by having aim animations that can go up to 180 degrees or by triggering turn-in-place animations more aggressively. So we're checking whether or not we're crouching. We have two different angle clamps based on whether or not we are crouching, and these are two-dimensional vectors, and essentially it contains the range of angles that we're clamping. So in this case, -90 to 80. We're breaking the vector 2Ds to get the x and y, so the -90 to the 80, for the example for the one we looked at. We're also getting this in root yaw offset up here, which is the input into the function. We're normalizing the axis, and we're clamping the angle between these values here. So although it might look complex at first, it's just a way of storing the minimum and maximum angle degrees in a single variable. We're also checking to see if the minimum and maximum angle are equal to each other. And if that is true, we just return the normalized root yaw offset. If that is true, we just return the normalized root yaw offset. We set root yaw offset with it. And it says we want aiming to counter the yaw offset to keep the weapon aiming in line with the camera. And so we multiply root yaw offset by -1 to set an aim yaw, which I assume is rotating the upper body. Our next step in our update root yaw offset function is to smoothly blend out of the offset. So the next step is that when we're in motion, we want to smoothly blend out of the offset. So if our root yaw offset mode is equal to blend out, or our gameplay tag is dashing, then we use a float spring interp function, which uses a simple spring model to interpolate a float from current to target. This is my first time seeing this node actually, and it's probably really useful. So we take our root yaw offset spring state, which is a custom, it looks like a custom struct. Let's see if we can't find that. Okay. Let's copy paste and let's does not look like it is giving me the option to break this up. That's unfortunate. Let's go ahead and so this is a C++ function, and I'm not sure exact. Okay. So we have this root yaw offset spring state variable, which is a spring, which is a type float spring state. And I'm not exactly sure what its function is or what it does. Unfortunately, this is a C++ function, so we can't easily open it up and look at it here. But it is just doing a float spring interpolation. And it's setting the root yaw offset from that. But let's try searching root yaw offset spring state. And unfortunately, it looks like it's not being set outside of this node, so it looks like this node takes it as an input and sets it from within the node. At least that's my guess. It doesn't exist as a local variable inside the function because it would be reset each time the function is entered unless it exists outside of the scope of that function. So that does make sense to me. Moving on, we need to next reset the blending out of the yaw offset each update. A state needs to request to accumulate or hold the offset, otherwise the offset will blend out. This is primarily because the majority of states want the offset to blend out, so this saves on having to tag each state. So we're just setting root yaw offset mode to blend out, and then if a specific state needs that to not be blending out, then they just set that there. So a very clean and elegant setup for the root yaw offset. And well, we've made it to the end of the event graph, and you might be wondering about some of the things that, well, don't seem to be complete. There are some variables referenced and that aren't addressed, that aren't set. There are other things that we probably need to do calculations for, such as all of our distance matching logic, but it's not here. And the reason for that is, and I'm not going to be covering that in this video, but if we just hop into one of these states here, well, each node here has functions that can be bound to it. Function on the initial update of the node, on when the node becomes relevant, and on the update of the node. So any logic dependent on a specific animation node being active or a state being active can be run from a function that is bound to that node. And we will be covering those in another video, a future video on this series. But here you'll see that in all these states, we're actually referencing another linked animation layer. But if we click that, it's empty because we're actually overriding the layers in this animation blueprint with the layers from other animation blueprints, one for each item the character can hold. And we'll be covering the parent, the main base blueprint for those, as well as the layer interface for it in the next video. Because before we circle back around to the rest of this event graph, well, lots and lots and lots of the state setup is put together there. So we'll hop over to there and then back to this one for this next video. Hope you guys found this video helpful. It was only a couple days ago that I checked YouTube and realized that no one else had been talking about the animation system, Locomotion system setup for Lyra, so I figured I would. Thanks for watching. If you enjoyed the video, be sure to like it and subscribe to the channel down below. It really does help out the channel. Thanks again for watching, and I'll see you all in the next video.